Given the parametric equations x equals 2 times the square root of t and y equals 3t squared minus 2t, we are asked to find dy dx and the second derivative of y with respect to x. So the first thing we would actually look at is what in the world is dy dx and how do you find it? So there is a lot of confusion sometimes between dy dx and dx dt and dy dt. So let's just take a look at this again. We have x equals 2 times the square root of t and y equals 3t squared minus 2t. So this is the x position at any given time t. This is the y position at any given time t. If I look at the derivatives of these separately, then dx dt will actually give me the rate of change of x with respect to t. So it's basically telling me how fast the particle or whatever it is moving left or right. Dy dt would give me the rate of change with respect to y, so that's how fast the particle is moving up and down, and both of these are at any given time t. So the question goes, how do you find dy dx? Well, it's a very simple fraction. If you look at this, you have dy dt divided by dx dt, and this is one of the beautiful things about this kind of notation. If you think you could do something algebraically, most often you can, and it's not really that you're going to do this manipulation I'm going to show you, or rather that that's why it works, but it does work and it looks right when you do the fractions. So when you have dy dt divided by dx dt, it looks like we're dividing by this fraction here. So if I do that and we treat it like a fraction, I would multiply by the reciprocal. So I have dy dt times a dt dx. And when you do that, your dt's are canceling out and you're left with a dy dx. So that is how you get your dy dx. Now dy dx is a different thing than dx dt or dy dt. This is the actual slope of the curve that the function is on. So this tells you how fast moving left and right, how fast moving up and down. This gives you the slope of the curve, and those are different. This one does not involve time at all. So you could look at the particle anywhere at a given spot and you're just drawing the slope. You don't know exactly how fast it was moving at all when it got there. Okay, so our second derivative, the formula says, okay, so now you've got this first derivative. We want to take the second derivative of this with respect to x. So we want a second derivative of our y's with respect to x. Well, the way you do that is you're going to actually take the derivative of this with respect to t. So you're going to do a d dt of your dy dx. And then you're going to divide it by a dx dt. And you're going to see that, and again, an algebraic manipulation that makes it look like this is what it is, but it does work. So this right here is implicit, okay, if you ignore this part right here, and you're going to see that, all right? So you can actually just do this derivative and divide by this, or you can do it implicitly, as I'm going to show you in the example, and you'll see why we divide by a dx dt. The important thing to remember is that the second derivative is absolutely not just the derivative of the derivative you get for dy dx. That is not the right answer. You are actually going to have to do something more to it. So onward to the problems. Okay, so to find our dy dx and our second derivative of y with respect to x, the first thing I would actually do is rewrite this. This is a 2t to the 1/2. So I know that dy dx, as I just said, is a dy dt over a dx dt. So what I'm going to do is take the derivative of y with respect to t, and that's very simple. It's a 6t minus 2. And then I'm going to take the derivative of our x with respect to t. So I'll multiply down, and I get a 1t to the negative 1/2. So t to the negative 1/2. If I were to simplify this, I would bring the t to the negative 1/2 up into the numerator. So this becomes a t to the 1/2. The negative exponents will change which side of the fraction bar you on, times the 6t minus 2. So that is a 6t, and I'm going to distribute This t is to the first power. This is a t to the 1/2. When you multiply, you'll add the exponent. So 1/2 plus 1 is a 3/2 minus 2t to the 1/2. So this is my dy dx. Now what I'm actually going to record is the nice version of this without the fractional, or if you had them, negative exponents. So this is a 6, and then your t is being cubed with the square root, minus 2 times the square root of t. So we have our dy dx. So what I'm going to do now is get to the second derivative, and I do that. My first step is to take the derivative of this, but I have t's here and I'm taking the derivative with respect to x, so my x does not match the variable that's present. So my second derivative, when I start doing this, will have some dt dx's in there. I'm doing it implicitly. So 3/2 times 6, we have 18/2 or 9t to the 1/2, and then that was a dt times dt dx, minus 1/2 times 2 is a negative 1t to the negative 1/2 dt dx. Now, no matter what happens, when you have t's for your dy dx and you take the derivatives, there will be t's here. So you will always have a dt dx. The only time you wouldn't is if you had like a plus 6 or something, then your derivative would be 0. So there would be 0 times a dt dx, and you don't have to worry about it. But every single time you're going to have a dt dx on every single term, so you should be able to factor it out. So I'll take the dt dx, factor it out, I'm left with a 9t to the 1/2 minus t to the negative 1/2. Well, I don't actually know what dt dx is, but I definitely know what dx dt is. So that's what I'm actually going to look at, is this t to the negative 1/2. But to change a dt dx into a dx dt, I'm actually going to turn it over, so I'm going to divide by it. I can bring it down into the denominator as a dx dt. And if you look at it this way, if I divide by a dx dt, that's like multiplying by a dt dx, so that is gone. So my second derivative of y with respect to x will be 9t to the 1/2 minus a t to the negative 1/2 divided by my dx dt, which was a t to the negative 1/2. And what I'm going to do now is just simplify this. I'm going to get rid of my fractional negative exponents, and I'll do that by bringing this t to the negative 1/2 up into the numerator. So it's a t to the positive 1/2 times a 9t to the 1/2 minus a t to the negative 1/2. Next I'll distribute. When you distribute, you'll add your exponents. So this is a 9t to the first, 1/2 plus 1/2 is 1, minus, and then we have a t to the 1/2 times a t to the negative 1/2. Well, when I add those exponents, I get 0, so t to the 0 is 1, and that is my second derivative, 9t minus 1. So you have a choice. You can just follow the rule, which says when you want the second derivative, just take the derivative again and divide by dx dt, or you could go through the process each time to kind of see why. But these are your answers. This one's amazingly simpler than that one.